The slides are visible?
Yes, sir. Visible, sir.
Okay, thank you very much. And first, I would like to congratulate this course coordinators for selecting such nice topic. So this deep learning, machine learning, its applications for speech signal processing. And in this talk, actually, it is a little bit different. It will give you the domain where you can apply these machine learning techniques or deep learning techniques for this speech signal processing. So that actually the conventional methods or conventional domains that we use for signal processing or specifically speech signal processing, they are time domain and frequency domain. And time domain actually tells us what are the signal values at different times, and this frequency domain tells us what are the frequencies present in the signal. And these actually two domains, they separately when you use them for speech signal processing, they are not actually able to handle this non-stationary nature of the speech signal processing, speech signal that we use for processing. So actually, there's a new domain that we call this time frequency domain. That is actually in the last few years, a lot of research has been done in this direction, where we combine this time domain and frequency domain together, and this time frequency domain can represent this signal actually in terms of energy as a function of time and frequency. And this domain, time frequency domain, that actually has got a new direction for machine learning, because the CNN kind of convolutional neural network kind of approaches, we need to have actually signal in the form of images. And this image actually this energy, that is a positive quantity which we represent as a function of time and frequency, which can be converted into form of image and intensity, and nicely that image can be used as an input to the CNN based classification for speech signal processing, and various applications actually, like a lot of work has been done in biomedical domain, where we have normal abnormal classes of biomedical signals like electroencephalogram signals, electrocardiogram signals. But in speech is also new domains, actually health related applications. They are coming like Parkinson disease, that also can be identified using speech signal processing, speech and processing can be done using this time frequency image and deep learning, machine learning methods. So even vocal related disorders that can be identified using actually this time frequency image kind of concept. So the main purpose of this talk is to explore you time frequency domain, and that actually then you can convert this time frequency domain, time frequency representation in the form of image, and that image actually you can use for this machine learning based speech signal processing or deep learning based speech signal processing, CNN, convolutional neural network based speech processing. So with this background, let us start this talk. So this is the overview of this talk. First, we will see transform. Then we will actually understand Fourier transform. Then after that, short time Fourier transform (STFT) will be explained, and then we will see continuous wavelet transform (CWT) and discrete wavelet transform (DWT), Wigner-Welle distribution (WVD), and Hilbert-Wang transform will be explained (HHT), and in the end, conclusion will be provided. So transform actually it is actually very difficult to find any area of science and technology these days where transforms are not actually used. It is like signal processing is also actually one kind of this like machine learning techniques. You will find signals everywhere, and the signals are also they have sometimes normal classes, abnormal classes, different classes, and nicely you can use transform domain to extract the information, and then we can use machine learning based approaches. So in general transform, this is actually mapping between two domains. So for example, like time domain to frequency domain, and we can go from one domain to other domain, and we do useful processing in other domain, and after doing that processing we can come back in actual domain. So in actually formal definition, we can say this is a mathematical operation which takes a function or sequence from one domain and maps it into the another one, that is actually like in case of Fourier transform, this time domain and frequency domain. So it is a bridge between, you can go from time domain to frequency domain, you can come back from frequency domain to time domain. And why we need signal transforms, because there are many reasons, and here we will highlight the most significant actually. reasons for using transforms. So first one is transform actually provides hidden information about the original function or the signal. So like what are the frequencies present in the signal, which frequency is a major frequency, which frequency the minor frequency. That information we can get from the transform domain. And this transform also help us to solve differential equations. So like generally in signal processing, the signals actually they are considered as the output of the system, and the system we use differential equations to represent the system, and where actually these differential equations they connect input and output of the system in actually in mathematical way. And then actually if it is differential equation of the less order or small order, then actually nicely they can be solved with the conventional methods. But if your differential equation has actually very high order, it is very complicated, then we have to go for signal analysis method, transform domain based, and this signal transforms help us to solve such kind of differential equation, which is actually complicated, for which we use for complicated system representation, or this differential equation at high order. So in such scenario, transforms are very useful to solve the system which is represented by the differential equation in order to understand the input and output signals of that system. And the third reason, this transform can provide data compression and storage may require less memory. So in actually signal transforms, we use basis functions to represent the signal, and these basis functions, if they are actually they have a structure similar to the say like signal, then actually requirement of coefficient or that we say transform coefficients will be less. And in other words, storage may require less memory. So the selection of the spoon depends on the type of food. And if you want to have noodles, then actually noodles are discontinuous food. And this fork, actually that is spoon that we use for handling such kind of discontinuous food, that is also discontinuous. So in similar way, if you have a selection of the basis function similar to the signal that we want to analyze, then actually the requirement of coefficient will be less, and storage may require this nice. That is actually that data, that is one of the concept behind this data compression. Another advantage of the signal transforms, one of the actually important concept of this time transform domain is that actually we can actually, when we go in other domain like frequency domain, then we don't have time. We have integrated entire time. So you are in such a domain, there is no need of time actually, and there is no need of depending on time, because frequency domain that is actually not depending on time. So many operations, for example, like convolution operation for linear time invariant system, that actually can be applied in frequency domain using this frequency using this convolution theorem, which can be like convolution in time domain is can be implemented as a in the frequency domain as a Fourier transform of the signal and impulse response of the system. So in that way, actually, convolution operation can be used to represent this LTI system, and where we don't actually need to depend on the time domain. So that is actually the beauty of the system, and you can implement signals in frequency domain, so various signal operation in frequency domain, transform domain. Then you can come back in the actual domain. The first transform that was actually proposed by the Fourier in 1807, that is actually according to this Fourier, any signal which is actually which is continuous or which is a finite number of intervals, and then actually nicely it can be represented with the in the form of sinusoidal functions. So this, like you can see nice example here, this prism. So this Fourier is actually working on the prism, and this prism can decompose this white light into 7 colors. Then actually this he thought that if you can represent this white light into simple colors, then we can also represent this complicated signal in terms of simple signals. So that was actually idea for this Fourier decomposition, and he represented this complicated signal in terms of simple signals. So Fourier work actually it was in 1807. This Joseph Fourier, that is actually he says that he means that all periodic functions can be represented as a weighted sum of the trigonometric functions. And this work actually was submitted for publication, and these three professors, Lagrange, Legendre, and Laplace, they were appointed as a reviewer, and they were well known, actually well known professors of that time. Lagrange is well known for Lagrange multiplier, Legendre is well known for Legendre polynomials, and Laplace is well known for Laplace transform. These three professors, they have concern regarding this Fourier work. Like Fourier was representing real life signals in terms of complex basis functions, and due to that, actually negative time and negative frequency was coming into picture. And other one, actually this Fourier was representing aperiodic signals that we realize in terms of periodic functions like sinusoidal functions. And these are the third one, this real life signals, they don't have negative time, negative frequency, but Fourier was using such kind of mathematical model which actually gives you negative time and negative frequency. So due to these reasons, these people, actually these professors, they denied his work for publication. And after 15 years, he's actually professor, they understood value of the Fourier's work, and then actually they consider that this is whatever Fourier is thinking, that is actually general form of the real space. That is, he was his space complex plane, and that is actually generalized form of the real space. So in that way, actually, this Fourier work was finally published, and even today, whatever transform we have, we actually understand with the help of Fourier transform. After that, up to 143 years, there was no significant work in the signal processing. And 1965, Cooley and Tukey, they come up with the actually algorithm that is known as fast Fourier transform, that can compute Fourier transform in efficient manner, and that is actually FFT algorithm. And so this Fourier transform and FFT, you are using FFT, you can implement this Fourier transform in the computers and the machines. And this Fourier transform, this complicated signal can be represented in terms of simple signals. So like these are known as basis functions, sinusoidal functions, non-functions, simple functions. And this Fourier transform, it is actually like a bridge between two domain, time domain and frequency domain. So one can go from time domain to frequency domain, and that is done by the analysis equation. And you can come back from frequency domain to time domain, that is done by the synthesis equation. So analysis and synthesis equations for Fourier transform are defined by these two equations. So first one is actually you are integrating time from minus infinite to plus infinite, and then you are getting this frequency domain f omega from the ft. Ft is the signal in time domain, and capital F omega, that is actually spectrum frequency domain. So here, when you integrate this time from minus infinite to plus infinite, so there is no time in the frequency domain, and frequency domain, whatever you have, that is actually doesn't contain any time domain information. And similarly, when you are doing this synthesis process, you are integrating frequency from minus infinite to plus infinite, so there is no frequency in the time domain. So time domain and frequency domain both are mutually exclusive. This is actually according to the Fourier approach. So this is the one example here you can see time domain and frequency domain. So in time domain there are three sinusoids, 5 hertz, 25 hertz and 50 hertz sinusoids frequency. And when you see the frequency domain, then you will have nice peak at 5 hertz, 25 hertz and 50 hertz. So that peak actually, so it some way this Fourier transform measures the similarity between the actual signal and that basis function that we use to represent the signal. So here you can see that at 5 hertz, so this means this signal has 5 hertz as a major component, others are minor components. Similarly, another signal that has a 25 hertz, that actually major component, others are minor, 0. And third one has 50 hertz as a frequency, this is like others are minor. So that is actually, so this Fourier transform can tell us what are the frequency component present in the signal, but it does not actually help us to provide any information about the time localization of these frequency components, what time, what frequency component is actually occurring. So in real life, when we use mathematical models to represent the signal, if any of the parameters is changing with time, then we call it non-state signal. If all the parameters are constant with respect to time, then we call them stationary signals. So this Fourier transform works well for stationary signals, but if you have a real non-stationary signal, then there is a problem. So stationary signal consists of frequency component which do not change with time. So all spectral components exist at all times, so there is no need of time information. And this Fourier transform works well for stationary signals. And non-stationary signals, they actually consist of time varying frequency components. So Fourier transform is not suitable for such type of signals. And for such type of signals, we need to determine time localization of frequency components. So that is actually motivation for time frequency representation. And here you can see nice example. So first signal is actually stationary signal, a signal with three frequency components. So here you can see at any point of time, these all actually three frequency components are existing. And when you see the Fourier transform of this signal, then you have 5 hertz, 25 hertz, and 50 hertz. These are the actually peaks. And if you see this signal stationary and these three frequency components, they are arranged in concatenation. So, like 0 to zero point 0.3, you have 5 hertz, 0.3 to zero point 0.6, you have 25 hertz, and 0.6 to 1, you have 50 hertz. So, these frequency, they are actually it is changing with time. So now when you see the Fourier spectrum of this stationary signal and non-stationary signal, then actually it is the same. So this actually this is the one of the major limitation of the Fourier transform. When you are classifying signals as stationary and non-stationary signal, then your spectrum is actually same. That is misleading because your signals, both our signals are different in the time domain, but you are getting same spectrum in the frequency domain, because frequency domain where you Fourier transform is not able to provide time domain information. So this is actually one of the important reason for going to time frequency domain or using this time information with the frequency domain, so that you can nicely represent non-stationary signals like speech signals in better way or in unique manner. So this motivation for time frequency representation, here we actually, what is happening in Fourier transform, the sinusoids or exponential that we use as basis functions, they are suitable for global analysis. So they stretch into infinity in time domain, and therefore they don't have time localization, because localization, resolution, concentration, that is proportional to 1 upon a spread. So due to this infinite spread, there is actually resolution, localization, concentration is zero. And these, on the other hand, there is instantaneous in frequency. So like when you see the Fourier transform of sinusoidal functions in the frequency domain, then actually they look like impulse. So they have actually perfect frequency localization. Spread is zero, so they have good resolution. So in order to have actually resolution in time domain, there is a need of time dependent frequency representation, which we call time frequency representation for non-stationary signal. This is also known as time frequency distribution. So the first approach that was actually proposed for this time frequency analysis, that was short time Fourier transform, HTFT. And this HTFT, actually what we do, we divide the signal into different segments, and each segment we assume that signal is stationary. Then arrangement, and then for that actually arrangement of the Fourier transform of these different segments gives us the short time Fourier transform. So here you can see actually the signal that we want to analyze, and W is the window function, and that is actually centered at T dash. So T dash, you are choosing different values of T dash. Actually, you can cover different parts of the signal. So that is actually window signal. Then you just come to the Fourier transform of this window signal, that gives you the short time Fourier transform STFT. So it converts actually this 1D signal, one dimension signal, to two dimension signal. So like you can use this image for your CNN or deep neural network for this classification of the signal or analysis of the signal. So here you can see this time is actually T dash, this is the time localization, time location or window location, and omega is the frequency. So this one dimensional signal xt, now it is mapped to two dimensional, so it's like function of time and frequency. So this gives you the time frequency representation of the signal. So this is just one example, like T dash equal -8, -2, different locations, 4, 8, and you can shift this window function, and then you can isolate that particular region which is actually covered by the window, and then you apply the Fourier transform. So in that way, you can have nice actually short time Fourier transform STFT, and then so this when you use this Gaussian window in the actually instead of the conventional window in the STFT, that actually gives you the Gabor transform. That is actually the best window, optimum window, because Fourier transform or Gaussian window is Gaussian. So that is actually only one unique function till today, which has same nature in any domain. So STFT is a complex quantity, and in order to represent STFT, we like square magnitude of the STFT, that is known as spectrogram, and this STFT linear operator, and spectrogram, which is the square magnitude of the STFT, that is actually non-linear. So spectrogram is a non-linear operator, and when you use this actually as Gabor concept, this Gaussian window, that actually gives you the Gabor transform. So here, this is one example actually the speech signal. Like if you speak MATLAB, then the signal looks like this in time domain. And now, actually, based on the window size, suppose if you want to have a good frequency resolution, then we go for narrowband spectrogram, which requires use of large window. Similarly, if you want to have wideband spectrogram, and that gives you the good time resolution, poor frequency resolution, that requires a small analysis window. So here actually, according to your application, we use actually large window. Suppose you want to have good frequency resolution. So here the formats present the speech signal nicely can be seen. On the other hand, if you see the wideband spectrogram, then this formats actually the frequency domain, they are blurring kind of thing is happening. They are merging to each other, so they are not easy to separate. So that is actually based on the application. We can select the size of the window, but once window is fixed and selected, then it is used for the all frequency component present in the signal, whether it is low frequency or high frequency. So this is the MATLAB code which you can use to generate such kind of spectrogram images, and then actually you can have a spectrogram, then you can convert into image, that is like one matrix. So spectrogram command is there in the MATLAB, which can be used. So it requires the function, number of FFT points, sampling rate, selection of the window, and how much overlap you want. Because if you are not overlapping this window, then there is loss of the information and there is discontinuity in the data. So we prefer overlapping also in the STFT based analysis. This is another signal, linear chirp signal, which frequency is changing with time. So here you can see it is changing instead linearly from the low to high. And that actually, there are two kind of window functions that we have used for analysis of this signal. One is narrowband spectrum, like large window, so which results narrowband spectrogram and window size 250 samples. And when you short window for analysis with the 128 samples, for example, here that gives you the wideband spectrogram. So narrowband spectrograms gives you good frequency resolution, and wideband spectrogram gives you the poor frequency resolution. So according to your requirement, actually one can use narrowband wideband spectrogram, and these resolution are actually connected or governed by the Eisenberg uncertainty principle. So like if you have good resolution time domain, then it means a poor resolution in frequency domain. On the other hand, if you have good resolution in frequency domain, it indicates that you have poor time resolution. So in the MATLAB, there is chip, some command is there. You can use chip also to generate such kind of signal. Then spectrogram, that will give you the spectrogram of that image. So shortcomings of the short time Fourier transform STFT, that actually STFT provides the time information based on the computation of the different Fourier transforms for the truncated signal using sliding window function. And there is a serious actually problem. There is no thumb rule which will suggest us what should be the size of the window and what is type of the window. There is a serious problem. So how to select type and size of the window is a problem. And wide analysis window provides poor time resolution and good frequency resolution. So that is actually, similarly, narrow analysis window provides you good time resolution and poor frequency resolution. So there is no flexibility to change the size of the actually window or type of the window. Once window is selected, then actually it is used for all frequency component present in the signal. If you have low frequency component, then you want to have wide analysis window. If you have high frequency component, then you want to have narrow analysis window. So that actually flexibility is not available in the STFT. So there are various window functions actually, that is Bartlett window, Blackman window, Bowman window, Chebyshev window, Hamming window, Henning window, Kaiser window, rectangular window, triangular window, Gaussian window. And here you can see in the MATLAB there is window command and you can generate such kind of windows. Then you can use this for signal processing or analysis using STFT, short time Fourier transform. And this one of the important thing here that actually this resolutions that is governed by the Heisenberg uncertainty principle. So here you can see delta t is the duration of the signal, and delta f that is the bandwidth of the signal, and this is product of the duration and bandwidth that is always greater than equals to 1 upon 4 pi. So for the Gaussian function for the Gaussian window that is equality holds. For other kind of actually other kind of window functions there is inequality. So this actually so it says that here there is you cannot have arbitrary this duration and bandwidth very low, or the time and frequency resolution very high. This is actually there is a limit. It should be this duration and bandwidth product is always greater than 1 upon 4 pi for a non-Gaussian window. So you cannot go below 4 pi. 4 pi. This is the constraint window that is. So this says actually this resolution, time resolution, how well two spikes in time can be separated from each other in the transform domain. Similarly, in frequency domain, how well two spectral components can be separated from each other in the transform domain, that gives the frequency resolution. So according to this uncertainty principle, this time and frequency resolution cannot be very high arbitrarily manner. So there is a rule which you have to follow, and if you are increasing one resolution, like for example, you are increasing time domain resolution, then it will decrease frequency domain resolution. Similarly, if you are increasing frequency domain resolution, then it will decrease time domain resolution. So based on that, actually, this wavelet transform that was proposed in the literature, and wavelet is actually flexible window. So like you can change. We look the signal from the scale point of view. So when you are looking at low scale, it gives you the compact window time domain, which is suitable for high frequency components. Similarly, when you are looking at large scale, it gives you the window which has actually poor time resolution. So that is actually suitable for low frequency component. So wavelet is a waveform of the limited duration that has an average value of 0, and comparison with the wavelet sinusoidal waves, say like Fourier basis functions, which that sinusoids do not have limited duration. This way, like sinusoidal functions, they don't have limited duration; they have infinite duration. But on the other hand, if you see wavelet, they have actually this finite duration. So they are highly suitable for non-state signals. They are like transient kind of signals. You can design such kind of basis functions. They are suitable for transient, that is not in the sinusoidal functions. So these Fourier basis functions, sinusoid, they extend from minus infinite to plus infinite, and sinusoids are smooth, and periodic wavelet tends to be irregular and aperiodic. So that actually that is useful for representing non-stacy signals. And this is actually a very nice example of this. You can see many foods better handled with a fork than a spoon. So like if you see this fork, nicely it can handle the noodles. So that is actually similarly you can generate such kind of basis functions using wavelength, which can do analysis of actually many signals. That is not possible with the Fourier, because you are then using low scale, you will have some kind of basis function, large scale you will have some kind of basis function, and middle scale you will have. So you have all possible scales in the representation, and we are assuming that at least one scale will match with our requirement. So it overcomes the fixed resolution problem of the STFP by using a variable length window function, and analysis windows actually of different lengths are used for different frequencies in wavelet transform. So narrow analysis window that is suitable for high frequencies provides good time resolution and poor frequency resolution that is achieved by the low scale. And similarly, wide analysis window that is suitable for low frequency components which provide you good frequency resolution and poor time resolution that is obtained by the large scale. So in that way, actually, we can obtain various skills that is useful for the analysis of the different frequency component in the signal. So this kind of actually method works well if the signal that is to analyze mainly consists of slowly varying characteristics with occasional short high frequency bursts. So like if your signal has low frequency component as well as high frequency components, then actually you can nicely analyze them using wavelet functions, wavelet transform. So this is actually mathematical expressions for this wavelet transform. Actually, the signal that we want to analyze, and psi t that is actually mother wavelet, and destroy the shifting parameter, and s the scale. And from that, actually, these are the 1 by under root s. This is the normalization constant. So this normalization constant ensures that this 1 by under root s phi t minus tau by s, this is known as total wavelets, and it ensures that 1 by under root s is normalization constant, ensure that the energy of the daughter wavelet and the mother wavelet that is actually equal. So this means that each daughter wavelet also can be used as a mother wavelet, and in that way we give huge library and nicely the analysis can be done. So here, when you integrate this, then S the scale toy the shifting parameter, and in the transform domain, left hand side you have this continuous wavelet transform as a function of scaling S and this translation or shifting parameter. So that is a two-dimensional representation. The scale can be converted into frequency. That is, scale is proportional to 1 upon frequency. So that is actually you can time frequency representation can be obtained using this kind of actually approach also. So this is one example how this window actually works in case of wavelet transform. So here you can see at low scale this high frequency, and that is actually here you can see the high frequency component in the middle, then you have low frequency and then high frequency component, and that actually this is the window, and nicely once for a given scale you design the window, then you shift this for entire analysis so that entire different parts of the signal can be covered. So here you can see this is the design window, and then we are using this for the analysis of entire signal. Then again at large scale s equal to 0.5, this window size is increased, then we are using the design window for the entire analysis of the signal. And then again we have key the scale s equal to 2, then you can see which is actually suitable for the low frequency components, and earlier it was suitable for high frequency component. So in that way, when you are increasing more high frequency, more scale, then you see in the second part that is highly suitable for this middle part. So in that way, actually, we are analyzing the signal with all possible scales. So at any point of time, all scales we are using for analysis, and we are believing that at least one scale will match with the requirement. So this is actually history of the multi-resolution property. So like time domain, this is this Fourier actually like whatever 1948 is Shannon represented signal in terms of impulses, and each impulse has actually good time resolution. Each impulse duration is 0, so that is the good time resolution. And here you can see this is actually in frequency domain. They have a very poor resolution, like 0 resolution. On the other hand, this Fourier case, if you see in the frequency domain, it has infinite perfect resolution because spread is 0. In the time domain, this has actually spread is infinite, so they have actually 0 time resolution. So this Fourier actually is known as the Newton of the France because he represented signal in terms of impulses, which actually in the frequency domain, which actually Shannon did in 1949 in the time domain. So that without knowing the sampling in time domain, actually he represented signal with the help of samples in the frequency domain. HTFT short time Fourier transform, which proposed the Gavel. So here you can represent the signal in terms of the basis functions, which has fixed time and frequency resolution. And wavelet analysis, you can see at any point of time you are using all possible scales, and that gives you multi-unit analysis. So here at this point you have scale, you have good time resolution, then poor time resolution, like that, poorest time resolution. So at any point of time you are using all possible scales, and which can give you different kind of resolution. So that is actually multi-resolution analysis. So that is the beauty of the wavelet transform. So this is the history of actually this wavelet. In 1970s, this Morlet, he was a geophysical engineer, and according to that, Windows 2 is generated from the dilation, compression of the prototype, small oscillatory signal that we call wavelets. And this idea actually that Morlet has proposed, that was got a lot of criticism for lack of mathematical proof. So early 1980s, this Grossman, who was theoretical physicist, he formalized the transform and devised the inverse transform. And this first wavelet transform, it was formally in 1984-1985, Mayer developed orthogonal wavelet basis functions with better time and frequency localization. And Ingrid Duvechi's, this is the proposed discretization of the time and scale parameters of the wavelet transform. In wavelet frames, she proposed in 1986 orthonormal basis of compactly supported wavelet, Duvechi's wavelet 1988. And Stephen Mallat is proposed the multi-use analysis with Mayer in 1986, and his PhD thesis was based on this kind of concept in 1988. And he also proposed the discrete wavelet transform and cascade algorithm for computing discrete wavelet transform. Martin Bitterly and Jelena Kovacevic, they have come a lot of work in this wavelet time transforms. They proposed wavelets and filter bank 1986. Perfect reconstruction of signals using finite impulse response filter banks 1988, and subband coding, multidimensional filter banks 1992. So this actually scalogram that actually we use from the wavelet transform. So wavelet transform may be a complex quantity. So for representation purpose, we take square unit of the wavelet transform, that is actually known as scalogram. So wavelet transform is a linear operator, scalogram is a nonlinear operator, and this kind of representation actually provides cost terms when frequencies are very closer. So how to compute scalogram in MATLAB? Then CWT command is there, and that's the signal that we want to analyze. Scales like scale range we define, and wavelet name we give here. Plot, then it gives you the scalogram in MATLAB. So here you can see this is the signal actually in time domain, that is triangular function, and it has all frequency component with the signal. But when you see this time scale domain, then actually it has at low scale it has good time resolution. A large scale it has actually poor time resolution. So that you can see all kind of resolutions present in the time scale domain. That is, if you apply STFT here, then you will not have this multi-resolution analysis. You will have fixed strip kind of actually representation in the time frequency domain. So this is the MATLAB code for getting such kind of actually results. You can generate signal using this command, s equal to 1 minus absolute t, and the CWT, that actually wavelet CWT, then you can use signal and scale range, then mother wavelet and absolute value. It will give you nice actually time frequency representation, time scale representation, then you can convert it to time frequency. So this is one example. Here you can see the signal is actually is decaying with respect to frequency, like frequency decreasing with respect to time. So first you have 30 hertz, 20 hertz, 10 hertz, 5 hertz, and then you see the time scale representation. Actually, its scale is increasing. So because scale is proportional to 1 upon frequency. So this time scale domain you can see, and each scale has different kind of resolution. So now, do you have any questions till now? Anyone has any questions, please? Professor Rakesh?
Sir.
Do you have to continue for 2 hours, or just break is required?
Sir, it is on you, sir. If you want to take rest, sir, you can take 10 minutes break. Otherwise, you can
Okay.
continue, sir. There's no issue, sir.
Okay. So, any like we can have 10 minutes, some like question answer, then we can start other parts.
Sir, better we can have 10 minutes break.
Yeah, yeah, fine, fine. Okay. So then we will meet after 10 minutes.
Okay, participants, if you have any question after the break, you can ask from the sir.
Yes, that will be better. Yeah.
सर आपका मेल विजिबल हो गया.
So sorry. Yeah, any questions, please?
Sir, I think there's no question, sir. You can continue, sir.
Okay.
Sir, one small question.
Yeah, please, please.
Sir, when we are talking like Fourier transform,
Yes,
that is the information
yes,
when it is time domain signal in time domain at every instant what the means instant of time what the signal information is. When
that is
transfer to Fourier domain, we are having frequency information, right?
yes, yes,
No time information. When we are coming to this wavelet transform,
yes.
that is after that that is STFT, right? That is short time Fourier transform.
It's
That means in a
before
fixed window
Wavelet
of
transform.
time, fixed window of time we are having information, frequency and whatever other things, amplitude, energy, right? In a fixed window, time window, STFT, right, sir?
Yeah. So in STFT, this instead of looking like a particular time interval, we are looking in time frequency domain both. So it is one kind of time frequency tile. So each basis function is representing tile in two dimensions, time and frequency. So you have some part in time and some part in frequency.
When it is something like yeah, putting a fixed size window on the
Yeah,
signal.
yeah, that is
A
fixed
time,
size of
fixed size, time window.
time window, but it is actually it is shifted by the this Fourier kernel. So you are shifting that in frequency domain also.
Frequency domain also. Yeah, right, sir. But when we
So
are talking about
before,
wavelet transform,
yes,
that means we are changing the shape and window size. Is it so? No? Shape. We are changing shape
shape is
as well as
according to
window size, and
according
then
to
shifting that window.
yeah,
Sir.
yeah.
Then here in the last slide, what that you have written scale and transformation. I need a little description of that. Yes, sir. In
This one,
that diagram, that slide in where, yes, sir. Time scale.
so
That
that
this
yeah,
slide is fine, sir.
yeah. So this is actually like in here we use scale function to represent the signal. So this is scale, each scale we design the window, and from that we want to analyze the this signal. So this scale actually this like each time we have different scales. So this is like a time scale domain, and this scale can be converted into frequency. So then in that way you can get time frequency domain also. But
Yes,
many
sir.
people are happy with
You can say
time
that
scale domain.
time frequency information. The scale, that frequency, that means giving frequency information.
Yeah, yeah, time frequency. So
So
that is
how
time
this
frequency.
scale and frequency are related, sir?
Yeah, that is actually very good question. So this is actually there is no this is based on the perception. So if you see like a scale, then actually it covers like you have large scale. So it covers large amount of data, so large duration. So in that way, that inverse of the duration gives you the frequency kind of like perception. It is just empirical. According to actually empirical study, there is a different relation between frequency and scale for different wavelets, and they come up with the different this proportional constant. So like a scale is proportional to frequency, and the scale is equals to k upon frequency. So the k is a proportional coefficient, a constant which has different values for different wavelets. So that actually we have to do experimentally that thing.
Right, sir.
In
Right.
it is right. So like if you see the less amount of data, low scale, then it is actually like it is like the frequency will be 1 upon that interval. So frequency will be high. That low scale is corresponding to the high frequency. This means large interval of the data. Based on that observation, this is actually defined.
Sir, one small
this example. Can you see this one? This example.
Yes, sir. Yes, sir.
So at first you have 30 hertz, then you have 20 hertz, 10 hertz, and 5 hertz. So suppose if you take the if you want to detect this 30 hertz or 5 hertz, so where you need large window. For 30 hertz you need large window
Yes, sir.
compared to 5 hertz. So 5 hertz actually that 30 hertz you need less analysis window, and 5 hertz you need wide analysis window. When you use wide analysis window, this for low frequency component, this means that its actually scale is large. So that is like large duration. So frequency will be less. So if you are using large scale, this means it is covering large duration of the signal, and which results low frequency. And you are considering small scale, this means less duration, high frequency component. Then based on that, this inverse relation has come.
Thank you, sir. Thank you.
Yes, you are asking some other question, please.
Yes, sir. That is when we are talking that this STFT or wavelet, so it is like window size varying, shape varying like that.
Yeah.
How it is different from windowing of that in Hamming window, Henning window. There also we are windowing the things, and here in STFT also we are windowing the signal. Then how we can differentiate meaning wise means what we are getting.
So in case of wavelet, that window.
Sir, in STFT or in wavelet,
Yeah.
ultimately we are windowing the signal.
Actually, this windowing is different. So like this is just for like if you will see this XT is the signal that we want to analyze with the mother wavelet is psi t. Then from that we shift and scale. That gives you the daughter wavelet, but it can be considered as like a delayed version and scaled one. Like tau, it is shifting by tau, and then we have scaling by s. So here actually this is like scale. So like when you have low scale, then this window will be compact in time domain. But window that is actually you are designing from the mother wavelet. In Henning in STFT, that window we are using, that doesn't use any scaling concept. That is just the main purpose of that window is to make finite signal. Doesn't have any effect on the scale. On the other hand, in the wavelet, there is scale concept, and which makes you actually scale dependent analysis. So your window will change the shape, will change the duration according to the scale that you are using. That flexibility is not there in the STFT. So short time Fourier transform based approach that is actually can be considered like as a special case of the wavelet, and wavelet can be considered as a more general form of the STFT. Fourier transform, FFT, Fourier transform having any window that is for static signal doesn't use any time dependent analysis. So that is actually in STFT, this window is actually every time we are using window, different point of time. In Fourier transform, we use only one time. That is the difference with these approaches.
Thank you, sir.
Scale is actually is very important concept that is not in STFT Fourier transform also. So like for example, if you see the legs of the elephant looks like a tree. If you see the tail of the elephant looks like a snake. Elephant is not a tree, elephant is not a snake. If you want to see elephant like an elephant, then you have to see a proper scale. So that actually that flexibility is not there in the Fourier transform in STFT. So this is a very good analysis where you can actually by using very low scale you can have window like impulse. If you use large scale you can have window like sinusoidal. So you can have any kind of window or basis functions which can limit the actually size of the signal according to various scales present in the data. And we don't know which scale is good. So that method will give you analysis from which you can select the best scale. Is it clear?
Yes, sir.
Any other question, please?
I think, sir, no question more. No more
Yeah,
questions.
no question. So this CWT continuous wavelet transform that actually that we have seen, if you want to implement this in computer, then actually it will require infinite memory, because this continuous parameter, continuous variables, they need to be discretized in order to implement the computer. So in order to compute CWT, continuous wavelet transform by the computers or machines, we need to discretize this continuous time scale plane. So CWT representation is a very redundant actually, so that we need to discretize them, and the discretization of the continuous time scale plane on a dyadic grade gives you the dyadic wavelet transform. So here, this continuous mother wavelet, that is like wavelet, daughter wavelet with these parameters, shifting and scale, can be represented with the help of these discrete parameters. So like this K and M, and here you can see this is the now a discretized daughter wavelet, and that actually we use, then it gives you the discrete wavelet transform. So here you can see nicely this discrete wavelet transform can be implemented with the help of filter banks. So the signal that we want to analyze, then we apply this to high pass filter, low pass filter, and then actually each part is downsampled by 2. So again we have this like first one is detail, second one is approximation, and then actually this most of the real life signals they include low frequency component. Low frequency components are dominant. So we again decompose this low frequency component into this low frequency, high frequency, and then downsample by 2. So in that way, this lowest frequency component known as approximation, and the highest frequency component that is known as details. And again, actually, this whatever components, like first level we get 2, and third level we get 3 this levels components, and then we apply the reconstruction. Reconstruction that actually can reconstruct the signal from the decomposed components. So that is actually like a Fourier transform. We have analysis synthesis. So here also analysis part is actually computed using these filters, and synthesis also actually done by the help of filters. So this is another way of actually implementing DWT, the whatever this filter banks explained, the same way. So each, suppose first level your signal is having length of 512 samples and bandwidth is 0 to pi. Then after first level of decomposition, we will have approximation, which where 0 to pi by 2 hertz frequency range and length is 256 samples. And this detail that is actually its length is 256 samples and bandwidth is varying from pi by 2 to pi hertz. Again, we decompose this 0 to pi by 2 hertz signal at approximation, then it will give you the detail and second level, approximate second level. And this approximation length is 128 samples, detail length is that is again 128 samples. Then again, you decompose this 128 samples of the data of this as second level approximation. So it will give level 3 approximation coefficients and level 3 detail coefficients. So each one of length of 64 samples. And if you connect them, concatenation, this A3, D3, D2, D1, then it will give us the length of the signal like signal. So 512 samples. So many actually places this wavelet decomposition is also has been used as like a signal decomposition, like using Fourier transform, DFT, discrete Fourier transform, because you have same number of coefficients, same number of like samples, whatever samples you have in time domain, similar number of samples you have in frequency domain. So this is one-to-one mapping. That is actually. So how to implement DWT MATLAB? There is DWT command. You just take the signal and then DWT, then wavelet name. That will give you the
Sir,
yes.
sir, my two small questions here, sir. Question number one: DWT, as different from CWT, here signal is discrete time, xn, right? And then we are passing it through high pass filter and low pass filter, and then downsampling by factor, right, sir?
Yes.
Why we are downsampling by factor 2 only? Any other means we can be downsample by factor 3 or 4 or 5 like that?
No, actually, this first, this like here signal, whatever signals you are taking here in input,
Yes.
that also may be continuous. So this is magic in the wavelet transform. It will actually be a scale functions like box kind of function, which will actually sample it automatically.
Yes, sir.
So
Yes, sir. Yes, sir.
that
Thank you.
also, and this 2 factor is coming due to dyadic sampling. So like scale we have considered, that is a equals to 2 power m. This one. 2 to power n k. And
So
this
what?
b is 2 to power kn. This tau is 2 to power kn, tau.
Sir.
And s is 2 to power k.
Okay, sir.
Scale is 2 to power k. So we are actually every level we are doubling the scale. So we are going from the complete representative of the signal to the approximation side. So due to this 2, this is coming here. If you use like a different kind of sampling, then different factor will come.
So theoretically, that is possible, sir. We can do like other way also. Is it so, sir?
That is known as actually we call it multi signal processing, multi-rate signal processing.
Multi-rate, yes, sir.
Multi-rate. So there you can use different kind of, even in SHOP 2 you can use 4 also. Also, it is multi-rate signal processing, and this is one of the special case of that. So this is dyadic sampling we are using too. You can use higher sampling rate also. Even many books, some books people are using n factor also, capital N. Then you can have any value of that. It can be generalized for any number.
Okay, sir. Question number 2 is, sir, here we are getting next slide, sir. Next slide, please. Here we are getting at level 1, at level 2 DWT coefficients like D1, D2, D3. What exactly D1, D2, D3 are? Are they magnitude?
They are not magnitude, they are the transform coefficients. Wavelet transform coefficients, and people take them in different way. The literature, people don't understand. Sometimes they are represented as a signal. This is the transform domain, and A1 is approximation coefficient, D1 is detail coefficients, but they are DWT coefficients.
Actually, yes, sir, they are DWT coefficient, but what exactly information from the signal it is, that I want to know, sir. Means we got something D1, we got A1. तो सर इसमें हमने सिग्नल से क्या एक्सट्रैक्ट, सिग्नल के बारे में कौन सी जानकारी दे दिया है सर?
A1 gives you the signal at actually large scale, approximation. So signal has different scales. It is like onion. You are removing different layers of that from the data, and then you are getting different scales present in the signal.
So actually में sir, this A1, D1 or A2, D2, they are not present inside the signal, or they are present inside the signal.
They are the decomposition, so analysis, like sinusoidals don't present in the signal.
Yes,
but
sir.
when you present in terms of Fourier, then you will get the coefficient of the sinusoidal functions. Similarly,
Yes.
these are the coefficients of the wavelets.
Yes, sir, I got it, sir. Thank you, sir.
Suppose you are in America.
Yes, sir.
And I will ask you from where you are. What will be your answer? Your answer will be, I am from India.
Yes, sir.
Because you are looking India at large scale.
Yes, sir. Yes, sir.
Suppose now you are in India, somebody asks you from where you are.
like you are from Haryana, like that.
Yeah. So
Again, entered in the Haryana, you are from Mendargarh, like that. Yes, sir, I got it, sir.
from which state you are?
Yes, sir.
From which state you are?
Sir, UP.
UP. So your answer will be Uttar Pradesh.
Yes, sir.
Now in Uttar Pradesh, somebody asked you from where you are.
Yes, sir.
What is
So
your
like
answer?
like from Noida.
Noida. So you are from Greater Noida.
Yes, sir.
If Noida somebody asks you from where you are, then you will say I am from this colony. Then
This
colony somebody asks from
yes,
this
sir.
house.
Yes, sir. Yes.
Then somebody asks from where you are. Then after that you don't know from where you are.
Got it, sir.
That is the lowest skill that you know.
Yes, sir.
So similarly, you have no entire world you have represented in terms of skills. Similarly, here also the signal we are representing in terms of skills.
Sir,
And
is there any rule
connection
to,
with frequency.
sir, is there any rule for a level of decomposition that we should go for 4 level, 3 level, or 5 level, 6 level, like that? Like finding D1, D3, D4, D5, like that. Is there
Any
number of levels? Number of level of decomposition?
there is no thumb rule. That is why new methods are there in the time frequency representation. That will be covered in the coming slides, where you will find such decompositions. There you don't need to specify number of levels.
Okay, sir. Okay, fine.
So wavelet transform, how to determine the number of levels, how to select mother of wavelet, that is a problem.
Yes,
So
sir.
there
Yes.
is saying in Hindi, जहाँ न पहुंचे रवि वहां पर पहुंचे कवि
Kavi.
और
Yes, sir.
उससे भी बड़ा है अनुभवी. So experience is very important when you are using this wavelet decomposition signal processing. Based on the experience, you can determine how many labels are required for
Yes,
the
sir.
representation.
Yes, sir. Thank you, sir.
So these are actually here using DWT command. You can use this. You can get the approximate details from the signal, and then these are the commonly used wavelets: Duvechi's, Har, and you can see this Duvechi is from the low scale to large scale, and Har also low scale to high scale. And depends on your nature of the data. If your data is actually a low frequency, data is continuous, then go for Duvechi's kind of wavelets. And if your data is discontinuous, then go for Har kind of wavelets. So these are the now we see some applications. So DWT decomposition that gives you the approximate details. So approximation is associated with the low frequency region, and high frequency part is actually represented by the details. So this is a signal, it has noise, and if you decompose using this first level, then you will get approximation and second one detail. So detail is associated with the noise, and approximation is associated with the low frequency component of the signal. Again, you can decompose this approximation A1 to other two components. Then again, you can remove the noise. So in that way, this concept iteratively, you can decompose this data into different approximate detail components. And according to your requirement, you can select some of them to represent the signal. And DWT actually also can be implemented in the MATLAB using wave menu command. So you just type wave menu in the command window, and you can load your signal. And in this example, you can see take the wavelet or DV5 for number of levels also you can select, then analyze. So full decomposition, 5-level decompositions. 5 level means you will get 6 components. One is approximation 5th level, detail at 5th level, detail at 4th level, detail at 3rd level, detail at 2nd level, detail at 1st level. So in that way, you can get 6 components from the signal that you are analyzing, and you can see this signal has various scales, different frequency components, and each actually level is having different kind of frequency component which are associated with the different scales. There are various applications of the wavelets which include compression, denoising, feature extraction, discontinuity detection, data analysis, which is biological data, financial data, and we'll see one by one all of them. So, like this is a signal actually. This we want to represent this signal using DWT. So here you can see the DWT coefficients, and most of the coefficients are nearly zero. Only few are significant. So that actually gives the concept of compression, And this is a perfectly considered signal that you can see 75%, 81%, 87.5%. Even you can see this 93.7% compressed signal, and this actual signal that actually you can see that is a compressed signal is coming actually near to the actual signal. So that is actually this is the beauty of this method. Most of the energy is represented in terms of coefficients, which preserves most of the energy of the signal. This is one nice example of this compression of electrocardiogram signals, ECG signals, which measures the electrical activity of the heart. And here you can see the ECG signal, and then compressed ECG signal, which to 50% coefficients are thrown, 75%, 87.5, 93.5%, and you can see in all these compression levels, this data, whatever ECG signals that actually you see, that is actually nicely preserved the PQ pattern, this pattern. That is actually the important requirement for the diagnosis of heart diseases using ECG signals. Denoising also can be done, and the signal actually decompose a sixth level, a fifth level. So there are the fifth level approximation, fifth level details, fourth level detail, third level detail, second level detail, and first level detail. And you can see this D1, D2, D3. These are these three these bands, but they are associated with the noise. So that actually can be removed from the signal, and that actually enhanced signal can be reconstructed. Discontinuity also can be detected using discrete wavelet transform. So here you have signal that actually have discontinuity but not clear. But when you decompose this into approximation detail at first level, then you can see the detail part is to show the discontinuity. This is that is actually beauty of the decomposition. Discontinuity also can be detected using this continuous wavelet transform CWT. So this is a signal, and when you see this time scale representation, nicely you can see there is a present of discontinuity. That is a particular scale also can be obtained from this CWT to detect the discontinuity at different levels. After that, there is actually another time frequency distribution that is known as Wigner-Weyl distribution. And Wigner received the Nobel Prize in Physics 1963, and he was from physics background, and Wille was from field of communication. It doesn't use any window function, no basis function. Is it works on the different actually approach. It is also known as classical time frequency representation, and it is an extension of the Wiener-Kinch theorem. So Wigner-Weyl distribution is a quadratic time frequency distribution which provides theoretically infinite resolution in time domain and frequency domain. And Wigner-Weyl distribution of the signal xt is defined time domain by this expression, and Wigner-Weyl distribution of the signal xt defined the frequency domain with this. So both actually they can be considered like first one is considered like a Fourier transform the time varying autocorrelation function. This gives you the power spectral density as a function of time. And similarly, this is in frequency domain. This is like time varying or frequency varying this correlation function. So that gives you the time varying actually nature of that power spectrum. So it's like equivalent in according to Parseval theorem. So we have like a nice theoretically good resolution in both domain, and we can without using any basis functions we can get the this time frequency representation. But here actually one of the serious problem in this time frequency representation, when you have multi-component signal, then it suffers from the cross terms. So like you have when you apply Wigner-Weyl distribution for this multi-component signal, then it has WVDs of corresponding auto terms and corresponding cross terms. So this is actually these cross terms actually create the serious problem in the Wigner-Weyl distribution interpretation. So sometimes it's misleading. So we'll see some examples like this is signal, some of two linear signal with positive negative chirp rates. But when you see in time frequency domain, that actually together with the this actual components, it shows the presence of cross terms also. Similarly, here also in the time domain, we have signal which is sum of two linear chip signals with positive chirp rates. But when you see the time frequency domain, which is obtained using Wigner-Weyl distribution, it shows the presence of three components in time frequency domain. So other one is middle component is coming due to this cross terms. This is another example. Here you see this signal is the sum of two separated bands of frequency components in time domain. They are time limited and frequency limited signals. When you see this time frequency domain, there is actually three time limited and frequency limited actually regions. So this middle one is coming due to cross terms. So the serious limitation of the Wigner distribution. Many actually techniques have been proposed in the literature to reduce these cost terms like Kandel design, wavelet decomposition, perfect decomposition filter bank, Fourier Bessel decomposition, image processing. And there are many actually methods here. Their method codes are available in this toolbox. So here you can see this Fourier Bessel decomposition based approach is used to reduce the cost terms. And here as you can see cross terms free time frequency representation can be used nicely. It can be used to get the cross term free time frequency representation using Fourier Bessel decomposition. Recently, not recently, like 24, 5
Excuse me,
years.
sir.
Yes.
Just use chirp signal. What is the exactly meaning of chirp signal, sir?
Chirp means actually it is generated by the bird sounds. Birds actually when they sing in rural areas, if you see, then we get such kind of signals. So based on these bird sounds, these chirp name is given. Chirp means sound of the birds. They are very commonly used signals like you will find at the radar signals, they are chirp signals. In communication also we use chirp jammers. At sonar we use chirp signals. Many places you will find actually chirp signals. They are commonly used signals in various applications.
That means
Bat
any
signal is
signal
a bat
processing
signal is a
characteristic,
chirp
sir?
signal. Bat signal.
Any like signal processing characteristics should be there for a signal to be defined as a chirp signal.
Chirp signal is one of the actually model that which we use for defining signal.
Yes, sir. Okay.
Yeah, there are many other models also. This is also one of the non-stationary signal model, where your frequency is changing linearly with time. Frequency also can be changing quadratic manner also. That is known as quadratic chirp. It can be third order chirp also. So depends on your application.
Yes, sir. Okay.
So, this 1998, this Hilbert-Wang transform actually has been proposed. So, it has actually two components. One is empirical mode decomposition, second one is Hilbert transform. So, empirical mode decomposition decomposes signal into monocomponent signals or intrinsic mode functions, and then we use Hilbert spectral analysis to determine their amplitude and instantaneous frequencies. So this HHT is actually is highly suitable for analyzing non-linear non-C signals. It has two parts, EMD and HSA. EMD method provides set of narrowband signals which are known as intrinsic mode functions, and Hilbert spectral analysis is used to compute the amplitude and instantaneous frequency of these individual IMF. So this EMD method is an adaptive method, data-dependent method, does not require any design of the base functions. It does not require any condition about the state and linearity of the data. And EMD method can decompose non-linear non-state signal in terms of IMFs, and each IMF satisfies two basic conditions. So to complete the complete data set, the number of extrema and the number of zero crossings must be the same or differ at most by one. The mean value of the envelope defined by the local maximum, local minima is 0. So these first condition ensure that your signal IMF is like sine cosine function, and second condition ensure that whatever IMF you obtain, that is like symmetric function. So these IMFs whatever we obtain using this EMD method, they are symmetric in nature, they are like sine cosine function, and it is very simple algorithm. So we determine the upper and lower envelopes of the signal using maximum minima. Then we determine the average of these two envelopes, subtract from the signal that we call residual. And this residual should satisfy IMF conditions. Not satisfy, then again we repeat this process. So in that way we obtain the first IMF, then we subtract the first IMF from the signal, then we get the another residual, then we repeat the same process till you get the another IMF, and this first two IMF we subtract from the signal and repeat the same process till we get third IMF. So in that way we get all possible IMFs from the signal, and this process is continued until the residue becomes a monotonous function, so from which further IMF cannot be derived. So this is very nice example, working principle of EMD method example. So like determine the maxima, determine the envelope, determine the minima, determine the envelope, and then take the average. So then we subtract this average from the signal, so it's a residue. Then again, this we have to satisfy this IMF condition, but it not satisfying, then we will repeat the same process. Determine the maxima, determine the envelope, determine the minima envelope, then average of that. So we repeat the same process. So after 7th iteration, you can see now you can get the residual whatever you have got. It has satisfying the conditions of IMFs. So this is the one example of empirical mode decomposition for healthy electroencephalogram signals. So here you have signal, and then you can decompose into different components: IMF1, IMF2, IMF3, IMF4, 5, 6, 7, 8, 9, 10, 11. So first IMF represent the lowest scale, present the data is like highest frequency component present the signal, and 11th IMF represents the lowest actually frequency or highest scale present in the data. So in that way, actually, you can have a wavelet kind of decomposition without determining the number of labels, without knowing the prior information about the number of labels, about the mother wavelet, and it has been shown in the literature that actually similar kind of wavelet decomposition EMD method can give, and there is no need of any condition, there is no need of any data requirement, there is no need of any assumptions, there is no need of any prior number of labels, no mother wavelet requirements. So just it is adaptive, you just give any kind of data, it will decompose into components, then we apply Hilbert transform to determine the amplitude of instant frequency, then we get the time frequency representation. So Hilbert spectral analysis, that is actually amplitude envelope instant frequency or IMFs are estimated using this Hilbert spectral analysis technique. So Hilbert transform will convert the signal into its analytic form. Xt plus I times its Hilbert transform gives you the AT to power I theta t. So that is AM FM signal, amplitude and frequency modulated signal, and this EMD method is actually considered a general form of the representation, where signal can be represented in terms of sinusoidal functions, but whose amplitude and frequencies are changing, varying with time. So like in case of Fourier transform, this amplitude and frequency parameters are constant, but here they are allowed to vary with time. So this is one example. Here you can see the synthetic signal, which has frequency 600 Hz, 700 Hz, 1500 Hz, and 1600 Hz, and there is no information about time, what time these frequencies are appearing. On the other hand, if you just apply EMD method, take the decomposition with the various IMFs, first to 7, then actually you get this time frequency image, frequency and time distribution. And it nicely shows that like 700 Hz frequency is occurring 2 times, 600 Hz frequency occurring 2 times, 1500 Hz frequency occurring 2 times, 1600 Hz frequency occurring 2 times. So there is actually nicely you can have, and this is actually this concept now people are using for machine learning, CNN, for this. And whatever I presented, this may be the first time in the speech processing you can actually explore these techniques together with this time frequency representation, time frequency image, time frequency matrix for speech processing with application of machine learning and CNN based approaches. So this is the conclusion of this talk. Time frequency representation is a general representation of frequency representation. Similar like non-state signal is general representation of state signal. And there are various problems in time frequency representation like short time Fourier transform, selection of type and size of window function, wavelet transform, selection of mother wavelet, Wigner wavelet distribution, presence of cross terms, Hilbert transform, no mathematical representation. So time frequency analysis is an active area of research, and this talk is based on these references. You please go through these papers references in order to have more detailed information about this talk. And this is just the initial work on time frequency, and now many new advanced techniques have come, like empirical wavelet transform, Hilbert ensemble empirical mode decomposition, variation mode decomposition. So there is one PhD thesis actually in our group, which is focused on the speech signal processing based on the variation mode decomposition. So I will share that actually presentation slides together with the slides to Professor Akis, and he will share with all of you. And please go through them. And I think with this presentation, with this explanation, you will be able to understand that actually that presentation better with this. Thank you very much. Any questions, please feel free to ask.
Sir, I have a little doubt here. One is a discrete wavelet transformation, second is the continuous wavelet transformation. Can you distinguish between two? One is the discrete signals, work on discrete time signals, and second is continuous time signals.
Actually, this continuous wavelet transform, where this scaling and shifting parameters, they are continuous in nature. So any continuous variable, if you store in the computer, it requires infinite memory. So between any two numbers, if it is continuous number, then there are infinite numbers. So that is not possible. Continuous wavelet transform is not possible to compute using computers because we need infinite memory. So what we do, we discretize these parameters and we compute this continuous wavelet transform on discrete points only, discrete values of the time shifting parameter and discrete value of the scaling parameters. That is actually discrete wavelet transform, and it nicely implemented using filter bank.
Yes. Sir, today we study the frequency time transformation basically in the
Yeah.
Fourier transformation. Frequency to time and time to frequency, both side we can transform. Sir, one more term I have listened. This is the spatial temporal transformation. Can you give just a brief idea about that?
Sparsely.
Spatial temporal transformations. It is also used in the machine learning and basically neural networks. I
Yeah,
think
actually,
space
like
and time.
sparse. Yeah. So some like we are looking for such a domain where you can represent signal in sparse manner. So this wavelet also can be used to get the sparse representation of the data. So sparse means you can represent with the less number of coefficients, more compact manner. So wavelet is also have application for sparse representation of the data.
Anybody have more doubt? Please ask participants.
Sir, one question.
Yes, please.
When we are talking about machine learning and deep learning training for speech processing applications, then we are saying that first convert into like a spectrogram and take the image, and that why not directly we are handling the data points of a speech signal?
That is actually there are two ways. One way is you extract features. Like for example, if you want to classify male speaker and female speakers, so
Right, sir.
nicely you can do with the pitch frequency, and sometimes overlapping, or that actually you can train the system and test like neural network can do. But suppose even sometimes like a vocal cord, vocal tract related disorders that actually can be associated with the features. So like this conventional machine learning also good choice because these features can be connected with the level of the disease and you can have more insight. And this but if you are not interested in this associating the disease label with the features and not interested in the interpretations, then just you want to do classification, then this CNN has come. Actually it's a new form of machine learning, advanced form, where you need to give data in the form of image. So this time frequency representation is actually is a platform which converts this one-dimensional signal speech into two-dimensional image that actually nicely can be handled by the CNN. So if you are interested in just for classification, no interpretation, then CNN is a good choice. And otherwise, you can go for machine learning based, where you can extract handcraft features, engineering features. Then you train the machine learning algorithm, then you perform the classification.
Actually, sir, when we are classifying directly data from speech signal points or finding the
Actually, then the speech is like you should have features like how do you identify people? Chinese people, Indian people, how do you identify?
all these features from a speech signal and other things
No,
we are
just
getting
one
via image
example I'm asking, how do you identify Chinese people and Indian people?
To their pronunciations.
from the speech.
No, speech is other like based on their face, nose size is different, eye size is different, no?
That is on the
Image.
image.
Image, but speech similarly, so such kind of features we can see from the speech also. So
Yes,
instead
sir.
of that, directly, if you take raw material, raw signal, speech signal, then actually you are not looking the features. Like Chinese people or Indian people, we don't see entire human body. We just see some set of features.
Sir,
So
actually, my question is
similarly, in speech also we can look the formats, we look
fine,
the
sir.
pitch
Formant
frequency,
frequencies, their formants,
yeah,
their fundamental frequencies, their pitch frequencies, like that. Actually, question is why we are going for a speech signal or those features via image processing to for training of deep learning or machine learning. Why not directly? Means why via image processing? Are we getting some additional benefit in this? Because unnecessarily we are making the system complex.
not complex. CNN actually, CNN is very good, powerful technique, convolutional neural network, where actually people give data in the form of matrix. And here is not time frequency representation. It is actually a unique representation of the speech, and it has lot of information. It's not complicated. You have nice formats. They are varying with time. Pitch is varying with time. You have voiced regions, unvoiced regions, silence regions. Many information is there. If your network machine learning technique will train with such kind of information, then the classification system will be more robust. Not complicated. These you have good computers.
Okay, sir. Okay. Thank you, sir.
Hello, sir.
Yes.
You have given a very good example of downsampling. I really appreciate that. Thank you so much for your valuable session.
Thank you.
Thank you, Tanuja. Sir, one more question I have. Sir, in the traditional speech recognition system, if we see the Fourier transformation is the core, because we extract the feature set using the Fourier transformations. Like MFCC, PLP, everything is dependent on the Fourier transformation. And if we go for the end-to-end system, sir, in today's scenario, we are training the machine learning systems or deep learning systems in the end-to-end models. Where we use, sir, it? Is it useful Fourier transformation in that systems, or we bypass it or directly train that system, sir?
Yeah,
Please
so
clarify,
that is
sir.
what actually this is speech is very redundant data. Like your speech sampling rate, for example, like even these days you sample the 16 kilohertz. So 16 kilohertz sampling rate means you have 16,000 samples per second. In 1 second, actually, you are collecting 16,000 samples. Even old time also, we have 8,000 samples per second, 8 kilohertz sampling. So sometimes actually even we are not doing proper signal processing. Then also due to this lot of redundancy, we are able to reconstruct this speech signal, or we are able to understand this signal, speech signal, because we collect lot of data actually. This, uh, but when you go for like more accurate, like intelligent systems like robotics, human machine interaction, then actually such kind of actually features, they are more accurate, they will be very useful. So now actually people are trying to connect with the machines, and they have very less memory, and you want to operate this speech-based robots in more like a reliable manner, more with less higher accuracy with less error. Then actually this kind of actually approaches will be useful. So this MFCC, all these are standard, like comparison, LPC, linear predictive coding, that also be used in the standards, recent standards in end-to-end communication. But more advanced techniques have come, but they are not part of the standards. So most of the techniques, they are based on the stationary, like linear predictive coding, LPC, FFT people use. They just old techniques, so people are still using in the in the standards.
Sir, you just said that you are, for speech processing, we are collecting a speech signal at the sampling rate of 16 kilohertz. That means collecting 16,000 data at in 1 second. And earlier we were collecting at 8 kilohertz. What additional things we are getting at 16 kilohertz?
You are having more data that because like earlier you have speech signals, now together with speech signals you have other signals also. So like you have cocktail party problem, you are in the party functions, so instead of the speech you can have other signals also. So we want all signals to be recorded. So now these days we have good samplers, good sampling, like 16 kilohertz, even 32 kilohertz also people sample, so that all sounds that is nearby that scenario all can be recorded. And this blind source separation during this cocktail party problem, independent component analysis, that is actually another area of research is coming, that people are trying with the machine learning algorithms. It is up to you, whatever you can take, like more samples means you are more close to analog.
Sir, more information we are gathering in that case.
So this world is analog, future is digital. What is the future of digital? Rajesh ji.
Yes, sir.
What is the future of digital?
The future of digital now, it seems to be infinite.
Again analog.
Again analog.
Yeah, because this world is analog. Because we are converting to digital because machines understand digital.
Yes, sir. Means everything now has to go via machine. So that's why analog to digital, again digital to analog.
So now I am speaking analog, you are speaking analog, but in the middle is digital. Everything is digital.
World gives analog and take analog.
Yeah,
but everything has to go via machine. And that's why digital.
So we want to have such a good digital representation which is close to the analog so that we can listen better.
Yes, sir. Thank you, sir. Thank you for this nice session and this all clearing the confusion and clarification for all the things in today's lecture. Thank you, sir. Thank you very much, sir.
Thank you. Thank you very much. Thank you.
Anybody have any question? I think all the questions has been addressed, and it is a good time to represent the gratitude to our expert. So thank you very much, sir, for this nice session. I really appreciate your expertise in the area of Fourier transformation, which is the backbone of feature extraction techniques in the field of speech processing and the speech recognitions. Today we learned different types of Fourier transformations with its advantages, disadvantages, wavelet transformation, etc. So hopefully we enjoyed today's session. I again thanks the expert Dr. Bilas Pachori on the behalf of our participants. Thank you very much.
Thank you. Thank you.
So nice of
thank
you,
you.
sir.
For this opportunity. Thank you very much. Thank you.
Thank you, sir.
Participants,
Thank you
please fill the
everyone for
feedback
attending.
form before leaving the
Thank
meeting.
you, sir. Thank you, sir.